Right, thank you very much. Thank you for the invitation to speak. I'm talking about some colouring problems in the reals, but I'll start with the naturals, where it's nice and simple, and gradually get towards the reals. And I'll do some background on the way. If you're very used to partition regularity, you'll be bored with the background, but I feel I ought to do it anyway. So I'll get to the main problem in stages. And when I do get to the main problem, it is joint work with Neil Hindman and Dona Strauss. Okay, so this is about somehow Ramsey theory with some additive structure. So let me start off with something that's a triviality, and by triviality I mean it follows instantly from Ramsey's theorem. So here's a statement. If you take the natural numbers and colour with finitely many colours, you can find an infinite sequence with all xi plus xj being the same colour. There exists, let's say, distinct x1, x2, and so on, with all pairwise sums without repetition. I'll get back to repetition a bit later on. With all xi plus xj, I not equal to j, the same colour. So why is that instantly from Ramsey's theorem? So here's the natural numbers. We've got colouring of the points of the naturals that induces an arbitrary colouring of the pairs by asking what colour is the sum. So I'll colour the edge from I to j. So I'm inducing a colouring of the pairs from the complete graph. The edge from I, I'll give the colour of the original colour of I plus j. Right. Ramsey says that's a colouring of the pairs of natural numbers, so there's an infinite monochromatic subset. That means a sequence x1, x2, x3, and so on, such that all edges between them are, let's say, red. And that exactly and precisely says that each xi plus xj, the original colouring, is red. So we're done. Okay, great. So instant from Ramsey's theorem. Right. And what you can say is that the system of equations xi plus xj is partition regular. Partition regular just means in any finite colouring of the naturals you recover a copy of your set. So you might say the system is partition regular. Now that's an infinite system. Just stepping back for a second, you might say, how about finite systems? So there are the many classical theorems of Ramsey theory which tell you that a certain linear system is solved in one colour class. For example, Schur's theorem from the 1910s. So I'm going to write that phrase there about 1 trillion times. So I'll just write it as WNFC, if that's okay. That's finely coloured. The claim is there exist x, y, and z of the same colour with x plus y equals z. Okay. Again, this is also not too hard to prove from Ramsey's theorem itself, by the way. And again, it says you take natural numbers, you finally partition it, in some colour class you find a linear structure. Oh, if you weren't sure whether or not we're including 0 as a natural number, you now know, since this is a theorem and not just an empty statement, a nearly empty statement. Okay, another example is van der Waerden's theorem. From about 10 years later. This is another example of a finite partition regular system. Whenever the naturals are finely coloured, there exists an all one colour, monochromatic, let's say an AP, a progression with k terms. So let's say for every k, this is the following statement, arithmetic progression of length k. So, but I mean, numbers of the form a plus d, dot dot, a plus kd. Where if you want to call that length k plus 1, I'm not going to object. Okay, and this is much harder. This you can't just sit down and prove from Ramsey's theorem. This needs some actual ideas to prove. Okay, so those are a couple of finite systems are partition regular. Not every system is. If I gave a system of equations, for example, x equals 2y, to claim that that's partition regular would be to say that in any coloring of naturals, I can find a number and double it of the same color. That's obviously nonsense. This is not partition regular. For example, you might say, what's the biggest power of n of 2 that divides my number? Is it 2 to an even number or 2 to an odd number? E.g. color by max the set of n such that 2 to the n divides x. I mean the parity of that, right? So you say it's red if I am 2 to an even number times odd, blue if to an odd times odd, and of course when you double x, it changes by 1. Or if you prefer, you could say you colour by how long are you when written in base 2, are you odd length or even length? That'll also work. So I'll say or max the set of n such that 2 to the n is at most x. I'll say colour, I mean because what parity of that, if it's even or odd. Okay, so not every system is partition regular, and I won't go into details now, but basically Rado characterized these. So in the 1930s, Rado found which systems, always of linear equations, which finite systems are partition regular. And he answered that exactly, if and if statement. It's roughly, it's everything you get from that and that by iterating them. So you can have a progression of progressions and a progression of progressions of progressions, and that's all you can get. So that's Rado's very nice theorem. I'll just mention briefly, which I'll return to later, that as a consequence of Rado, you can ask the question, what happens when you go to a different space? So this is here the ambient space is the naturals. What if I extend to a different place where linear structure makes sense, like Z or Q or R? So you could talk about partition regular over the naturals. That means when you find naturals, if I find your object, you could talk about partition regular over Z. Now, this time, there's no dispute. 0 is an integer. So what this means is when you colour the non-zero integers, there's a common copy of your thing, partition regular over the rationals, partition regular over the reals. There are 4 different notions. Now, of course, if you are regular over the naturals, you're trivially regular over the integers, because if I give you a column of the integers, I ignore the negative ones, look at the rationals, the positive. So this implies that, implies that. This one's actually an if and only if. So this way works as well. Let me tell you why that is. So at various points I'll say, here's why something is true. I'll tell you why it's true. If you're bored or sleepy, you're free to ignore my little mini explanation. Okay, anyway, here's why that's true. So I've got to show you why, if a system is bad over the naturals, it's bad over Z. Right? So I've got to say, given a bad colouring of the naturals, no solution of your equations, can you find a bad colouring over Z? And here's what you do. So here are the naturals with some colouring C that's a bad colouring. You can't solve equations. What you do is down here on minus n, you use the exact same C. Let's say this was K colours. The exact same C, but with K new colours. So if up says the colouring was, you know, red if prime, blue if composite, on the negatives it's the same, but it's pink if prime, some unnamed colour if composite. Okay, now if you had a solution of your linear system that was monochromatic, then it would have to live, all the x's would have to be either pos or all neg, the different colours. If they're all positive, contradiction. If they're all negative, use the exciting fact if you have some linear equations, which we have, if you have a solution of them, minus its also solution. Great. So that's just fine. From here to here, again, just in the finite world for a bit, that works. There's a kind of compactness argument that says if you can wreck your finite system for each finite part of Q, you'd wreck it in Z. So this happens to go as well for finite equations, for finite systems. I'll return to infinite later. And this one also, this one is also the implication, again, finite systems. And this isn't so obvious. This is because you can take Rado's theorem and check it also applies over the reals. The proof also works. So you get no, so it's not because of some nice, lovely one-line argument, it's because you have to check that Rado's theorem works over the reals as well. Okay, so these are always the same for any systems that are all finite or infinite, and these, so far I've mentioned, is just for finite systems. Okay, I'll return to that in a little while. Okay, so back to our linear systems of equations. Finite ones are done by Rado, so onto infinite ones. We've got that trivial one there. So how about a non-trivial one? Well, how about a non-example, first of all? You might say, this is almost an infinite set X plus itself, except it isn't. I didn't allow a thing plus itself. So you might say, you might ask, how about X plus X for some infinite set X, by which I mean all xi plus xj, even allowing I equals j. So if you think of the sums, so if a set A plus set B means all sums you can get, if I said to you I want an infinite set plus itself, that says all xi plus xj for all I and j even when they're equal. That is very easy to see doesn't work. Here's what doesn't work. Suppose you take your sequence, by taking a subsequence, it may as well be increasing, remember in the naturals, so x1, x2 and so on. Go to x 1,000, something pretty late. Now we're supposed to have that x 1,000 plus x1s in our family, but so is x 1,000 plus x 1,000. That is roughly double that, if 1,000's big. Now, I wrote down a colouring that wrecks the statement, this is exactly double that. It's very easy to similarly wreck, this is within 1% of double that. Right? For example, here we said, how long are you written in base 2? Ask how long you're in some shorter world. So here's a picture to wreck. So I'm trying to find you a finite colouring that never ever has two things of the same colour, where the big one is within 1% of double the small one. Why don't you just look at, say, log x. So in that colouring there, log to base 2 of x, we said colour the interval, this first interval all red, next interval length 1 blue. Let's just take intervals of length, say 2/3, and use 3 colours. So we have colours, which we do. And then they repeat. Okay. So again, saying one number is roughly double another says the log is about 1 more than log of the other one, right? It's within 0.9 and 1.1. And that's trivial to rep with 3 colours. Just go in blocks of, say, 2/3, and whatever number you have, if you roughly double it, I add 1 to the log, you're in a different colour class. Because 2/3 isn't whatever it isn't. Yep. You might say, that's 3 colours. You can almost do it with 2 colours. If I said to you, I want a class that's very small, you'd say, fine. Again, work with log x. You could say, have intervals of length 0.99, 0.99, that's red and blue, let's say. And then a teeny little interval that's green of length 0.02. And off you go again, same again. 0.99, 0.99, so long red, long blue, short green, and so on. So you can actually, if you wanted to, you can have 3 colours. One class is pretty small. The reason I mention this is this sort of strange, a weird digression. So for almost any notion of small you can think of, you can find a 3 colouring that wrecks that system of x plus x, which one of the colour classes is small. No one knows if this happens for 2 colours, but that's called Owing's problem. Owing's problem. And in some sense, who cares? Because you really care about finitely many colours anyway. But it's pretty. This should be a 5-minute thing to answer, right? So you only had 2 colours, so no little residual extra class. Is it true or false that if you 2-colour the naturals, you can find an infinite subset that's monochromatic? Or in this language, you can find xi plus xj with all I and j allowed. That's it's a very strange problem. Not linked to anything else, just odd that no one can solve it. Okay, so that was a non-infinite system. The most interesting system is Heinemann's theorem. So again, when the naturals are finely coloured, his theorem says you can find a sequence such that all the pairwise sums and all the singletons and all triples and all fours are all the same as each other, such that the entire set, finite sums from x1, x2, and so on, is monochromatic. Where this means what you think it means. It means finite sums. So things like x1 plus x3 plus x17. Okay. In the modern viewpoint, this comes from thinking about beta n. So the original proofs were very long and involved. The modern way to think about it, you look at the stone-shaped magnification, you prove something interesting about it, and that's like a 1-line deduction. Okay. That list of 1 theorem is almost the entire list of all infinite systems that are known to be partition regular. So there are a few more. There's one called Millikan-Taylor, which essentially, if you know how to prove Ramsey's theorem by a repeated pigeonhole, you can prove Millikan-Taylor by repeated Heinemann. So it's basically a similar kind of flavour. There's other things called central sets, but there isn't a huge stock of examples. There's a long history of people conjecturing, wouldn't it be nice if this system was partition regular? And then someone says, oh yes, here's a bad colouring. So every nice conjecture has been false. People would love to find a thing like Rado, some kind of if and only if condition that says, when is an infinite system partition regular? But so far, everything just doesn't work. Because for every conjectured thing, someone's always said, no, that system there isn't partition regular because of nasty colouring. So that's generally wide open, and say there are really very few systems known. If you think of a system at random, the answer is it's going to fail for some, maybe hard to think of colouring, but it's going to fail in general. So there aren't many examples known. Okay, so that's something like infinite. Now, how, in the infinite world, how do things vary with ambient space? As always, if you are PR over a small space, that implies over a bigger space, trivially. And the argument I gave for Z versus N didn't involve system being finite movement. That still works, so they're still the same. Now, over the reals, it's different, it turns out. I'll do an example now. And this example is basically because the reals are just too big. So I'll do a system now that is partition regular over the reals, but not over the naturals. And it's not, if you're familiar with a few basic theorems of Ramsey theory, it's not a very hard example to think of, but I'll mention it anyway. So this is a system now that is PR over R, but not over the naturals. Okay, I'll tell you what the system is. The system is, I've got variables called x's and y's. My system is y1 is x1 minus x2, y2 is x2 minus x3, y3 is x3 minus x4, and so on. Okay, so I want all the x's and the y's, they're all have to be the same color. Okay, so my variables are the x's and the y's, and my condition is that they're all the same color, and also y wants to move with those two. So if you prefer to set them with the x's, the statement is, you would like to find, the system is, some x's which are all, let's say, red, such that also x1 minus x2 is red, x2 minus x3, and so on. Okay. Now, over the naturals, this isn't PR, because even with one color, there's no solution, obviously, right? Because this decreasing is sort of bad somehow. Over the reals...
So are the x's increasing? Are they supposed to be increasing?
I didn't say, but since they're in the naturals, since y1 is a natural, therefore x1 has to be bigger than x2. So it follows from, it just follows just from the equations that they have to be infinite decreasing sequence. Okay, so it's just as linear equations. And all I'm saying is, for very silly reasons, this isn't PR over the naturals, because in any colouring naturals, there isn't a monochromatic solution of this, because colourings aside, you can't solve this over the naturals, because the y's existence forces the x's to be decreasing. Okay, so it's kind of silly. It's not a colouring statement in a way. Right. So the natural has no chance. Over the reals, well, what do we do? So here are the reals. Let me induce a colouring of the pairs by the colour of the difference. Sounds sensible. Okay, so I'm going to colour pairs by the colour of difference, and we know a lot of things that happen with structure. For example, Baumgartner-Heinel says for any countable ordinal, I can find not just a monochromatic subset, but one of that order type. So do it for omega plus 1. Okay, so by Baumgartner-Heinel, you can find the following: an increasing sequence, A1, A2, A3, and a point above them all, A omega, such that all edges in that set of cycles are all the same, they're all red, all edges are red. Okay. Now, how does it help solve our problem? I'll tell you what the x's are. My first x is A omega minus A1. No, thank you, sorry. My first one is A omega minus A1, that's better. So that's going to be x1. That's red, isn't it? My second is A omega minus A2, that's x2. My third, A omega minus A3, x3, and so on. And observe the x's are all red. And observe also that if I take, say, x3 minus x4, that is A4 minus A3, which is the red as well. Okay, fine. Tick. So that's somehow because the reals are just too big somehow. Okay. Just by the way, you might say, fine, that shows this isn't that. Where does Q fit in? I'll just say that for this system, this is actually not PR over Q. So it's bad over Q as well. So now comes a digression about the rationals. So it's another digression. In general, when you have a colouring that wrecks things over the naturals, there's a kind of easy crank to turn to wreck it over sorry, I'll say it again. When you have something that fails over the naturals, we had an easy thing to wreck it over the Z, namely just copy it on the other side. And there's a kind of easy, obvious thing to try and do over the rationals, which is to write numbers, okay, not in base 2, so they wouldn't terminate, but in, say, factorial base. So given a rational, say a positive rational, just write it in your favourite sensible way that terminates. Like a number plus something over 2 plus something over 6, something over 24, in some kind of base which terminates. So for x in Q, I can always write x as, say, 5 plus 1 over 2 plus 3 over 6 plus 1 over 6 plus 3 over 24, something like that, right? I can write it as A point B, C, D, E, where this means B over 2 factorial, this means C over 3 factorial, and so on. Digits are 0 and 1, 0, 1, 2, and so on. And who cares what I do? Just say that terminates. Okay, now, let's see how to use that idea. We saw that the system x plus x, remember that meant all xi plus xj, we wrecked it over the naturals. How do you wreck it? To wreck it over q, what do you do? Over, say, positive q. Here's what you say. You say, imagine your sequence of numbers. So suppose you did have this amazing sequence, x1, x2, and so on, with all xi plus xj in the same colour. And we're going to do stuff to wreck it one by one. So think about where x1 ends. Something point, some stuff. Maybe x2 ends a bit later, some end earlier, and so on, written in this funny way. Now, if they would all end by the same time, then that set would live in inches, wouldn't it, by multiplying up. So I can wreck that happening by taking my bad kind of integers and sort of scaling up. So I'll color like that originally, the biggest power of 2 that divides it, whatever, to wreck that happening. Okay, therefore, with log, they end later and later. And now you say, when a number ends, let's consider, say, x2 plus x1 versus double x2. They both end round about here, plus or minus 1. The way x1 plus x2 ends equals the way x2 ends, of course, because when you add them, no carrying happens over there. And the way 2x2 ends, it's sort of double how this thing ends. So you go and you think of it and you find, okay, I'll colour by the parity of the last digit, and it might not work if the digit place is an even digit place. So you say, okay, I'll colour parity of the last 2 digits and check that works. So some very similar kind of thing works. Just if you want to check it, you will check, you will find it works. Perhaps you look at the last 2 digits, maybe the last 3, you wreck it. And for every system anyone ever had that failed over natural sum colouring, there was always an essentially trivial extension like this that wrecked it for the rationals. Factorial base, or perhaps some superfactorial base, some mumbling about must go off to the right, comma, look at the end, comma, we're done, something like that. So it was sort of generally believed that probably these are the same systems, but actually it's not true. So as a result, it was recently shown by Barber, Hindman, myself, and Strauss that there are actually there are systems that are good over Q but bad over Z. So there exists a system regular over Q but not over Z. Which is quite a surprising thing. Okay, right. Let me now return to, I think, the main thing I want to talk about. I want to go back to our friend x plus x. We know that over the integers, there is no chance for 3 colouring. Over the rationals, no chance, by the same 3 colouring and some rubbish about even odd ending. How about over the reals? So how about x plus x over R? In other words, the question is, you finally colour R, can you always get the set of all xi plus xj, just for any I and j, monochromatic? So one's tempted to say that it should be similar to naturals, that of course if your sequence goes off to infinity, then it can't happen. Right? If your sequence goes off to infinity on the number line, then eventually x 1,000 is much more than x1, so this plus that's about half of double that, you wreck it as before. If they tend to 0, you wreck it as before. Double this. The trouble is they might tend somewhere. And that seems to cause problems. Right? That's true in the rationals as well. That's why in the rational we have to go to factorial base to kill it, rather than killing it here. Okay, so this is the main thing I want to talk about. And what we can do is, we can answer this, and the answer is, I want to say as you would hope, but as normally in these things you hope that it's the same in naturals and other places. So as you would hope, or perhaps not hope, there is a bad colouring, but only with CH. So our theorems are going to be, there exists a bad colouring, but only with CH. And we don't know what happens in general. So I'll just talk a bit about how this proof works. There's a technical bit which is long, which I will definitely spare you. There's kind of a slightly fun thing that happens after technical, which I will show you. And then the question will be, can you remove CH? And then it turns out there's an even more general question to ask. Okay, so that's the question then. We've got to find a colouring of the reals so that you can never find an infinite sum set that's monochromatic. That's what we'd like to do. Okay, so for Q itself, as I said before, that's no problem. You can do it in, I think, about 12 colours, let's say. The 12 being the 3 for the colouring that stops them ending at the same place, and then the parity of the last and second last digits. Okay, now, let's come at this gently. What's the reals? Of course, it is Q to some big power. Like, well, the reals. Q to the power of some kappa. By this I mean direct sum. So I mean a direct sum over I in kappa of copies of Q. So the vector space is the basis of that size. Right, so that's what the reals is. And of course, this statement, wherever it is, x plus x, mentions only the additive structure. So it's really only a vector space question. Right? There's nothing about topology involved. I'll mention at the end what happens if you bring in the topology. But at the moment, it's just a question about colorings, so it's just a question about big dense spaces over Q. Okay, so let's try and get the gentlest. Q to the 1 we've dealt with. Okay, now if you go to say Q squared, no surprise, you can do a kind of product argument and do it in about 12 squared colors. I'm sure you believe me, it's pretty easy to do. And then Q cubed, you can get with 12 cubed colors. That's all very well. Of course, that doesn't help you very much if you're trying to do, let's say, Q to the omega. Right? And we're trying to get to there gradually. Q to finite number, no problem. We'd like to Q to the omega as a good start. And this is not going to help much. So it turns out, and this is that's long and technical, I will spare the details. It turns out that actually for every number m, there exists a 36 coloring of Q to the m without an x plus x monochromatic. And who cares what that number is? All I care about is it's not 36 isn't a function. Yeah, 36 isn't a function of m, right? So it's a fixed thing, and that's actually a pretty hard thing to prove. But just believe it. I don't want to show it now. It's late in the day. Anyway, okay. So that's good. Right, now comes the fun bit. Of course, these colorings differ as m varies. So I now want to try and put them together. So here's how, let me now try and do Q to the omega. Where, of course, by do Q to the omega, I mean find you a finite coloring of Q to the omega without a monochromatic copy of x plus x. Okay. So what's a typical point in Q to the omega? It's an omega tuple with rational entries. So, 5, 1, 3, 0, 0, minus a half, 0, 4, and somewhere it ends. Okay, so let's imagine our sequence and think what it looks like. Well, let's see how to do our colouring. So think about our sequence. x1, x2, and so on. Now, of course, where they end can't tend down beyond 0, so part of the subsequence, it's either constant or it's increasing. It trivially can't be increasing. Here's why. Suppose that x1 is this one, and x2 goes a bit further, then let's compare x2 plus x1 and 2x2. Think how they end. They both end in this place here, don't they? In the same place. x2 ends with a 5, but 2x2 ends with, sorry, x2 plus x1 ends with a 5, but double x2 ends with 2 times 5. So we can rect that by our original very easy colouring, which is rect y equals 2x. Right? So over the rationals you say, what's the biggest power of 2 that divides it, positive and negative parity? Okay. So we'll always have that 2 colouring around. We'll always colour by, take the last thing in your expansion. Use the word support. Right, so it's the last thing in support. Excellent, good, thanks for preparation. If it's, in the normal sense of support, exactly, yeah. So we'll always use that colouring straight away. Okay, having done that, we now know that all our things end at the same place. Now, if they all end at the same place, that is some place, they all end here, that is some place m, some natural number m. But we know there's a 36 colouring of qm without a solution of x plus x. So here's our colouring. We're going to have 2 times 36 colours. Here's how you colour a typical unknown vector. You say, first colour by the 2 colouring of its last entry, and then you say, if its last entry is in place m, colour by your fixed reference colouring of q to the m. Okay? And then in that colouring, we're now done. Because again, take your supposed sequence x1, x2, x3, and so on. Where do they end? They can't end in different places, any of them, because of our thing about our x and 2x. Therefore, therefore they all end in the same place, but that's impossible because the ones that end in position m will all colour the same way with the same fixed 36 colouring. Good, so that's q to the omega, right? What's next is q to the omega 1, of course. So let's do q to the next interesting case up, q to the omega 1. What do? We say, take your supposed sequence, which we'll colour as we go along gradually. What do we know? It's some big transfinite thing which ends somewhere. Let's say it ends at time alpha for some countable ordinate alpha, say with a 4. Right. Now again, if you had 2 x's that end in different places, you could wreck that by saying, let's first of all, for all time agree to whatever else we do, colour anything by, take the last thing in its support. I've got to say, of course, remember, it's just direct sums, so supports are finite things. So there is a biggest one, there's no problem with that. Colour by our famous 2 colouring of the rationals that rect y equals 2x, and that by itself guarantees they all end in the same place. Good. So that's 2 colourings, 2 colours times what's going to come next. Right, what comes next? They all end in the same place, don't they? So they all, with different values maybe, they all live inside q to the alpha. Yes, but that is isomorphic to q to the omega. Right? It's a different isomorphism as alpha varies, and those don't nest, of course, but that's okay. For each fixed alpha, that's got q to the alpha. So we use our 36 kind of q to the omega. So we're done. And again, here's the argument again. Suppose you have a sequence, x1, x2, x3, monochromatic. Because of the way we coloured the last digit in our 2 colouring, they all end in the same place. Call that place alpha. Then in particular, we have coloured all of these things by our famous reference colouring of how they work in q alpha, which is the same as q omega. So it's quite strange. So each time we got upper cardinality, we double the number of colours. It's sort of a uniform bound.
2 times 36 or 4 times 36?
Oh, I'm sorry, 2 times, thank you. 2 times the previous one, thank you, yeah. So in general, that's why I need those things over there. If I have, for all cardinalities less than kappa, if I have a fixed bound number of colours, then I can do kappa with a bound of double that. That's why it was important to get that working nicely. So we're okay up to but not including omega to omega. Sorry, up to but not including omega sub omega. There we fail. Because we'd say for omega sub n, we can do it nicely, but with more colours, so we don't know. So in particular, we're done if the size of the reals is less than aleph omega. In particular, therefore, done with CH. Okay, so we're sort of great, happy, we're happy to have CH, that's great, we're happy. We're much happier to remove the CH. And the problem is, this method we think is doomed to failure. We can't see any way to get to even omega sub omega. Okay, I know the reals can't be said exactly that, but we can't get beyond that in particular. Right? And in a similar way, here's something we don't have, which would be nice to have. We know no way of saying, here are some colorings of finite powers of Q with more and more colors. Here's a machine that makes them do a bad number of colors. Because our statement here is just a different proof. It doesn't use those, it uses different colorings. So we have no machine or gadget that works over here. So we'd love to say we can do omega sub n, or aleph n if you prefer, in 2 to the n times 36 colors, therefore we can cut, but we don't have to do that, so we're stuck there. Actually, the following took us an embarrassingly long time to think of, the following question. Since we're looking at powers of Q, why stop at the reals? I mean, the following could be true. It could be that for every kappa, even bigger than the reals, could it be there is a bad colouring of Q to the kappa? Again, bad. Surely that can't be the case, but we can't disprove that. So for all we know, it's true, not because you get up to aleph omega and the reals are small, but because for every kappa, even 2 to the reals, that happens. So I think all three of us would strongly believe the answer should be no, that when you're big enough, you shouldn't be able to have bad colorings, but we just don't know. I'll finally briefly mention the question of what happens if you if you bring in the real topology. So suppose you insisted that each color class is measurable. Or maybe you'd rather say property of Baire. In that case, we can prove that the theorem, the system is position regular. That's a different thing. So in other words, every coloring is good. So the theorem says, if you are talking about measurable colorings, then the system x plus x is position regular. That sounds a nice result, but so my personal view is that all such results, they may be hard, but they're inherently quite boring. They all results, as far as I know, about additional multiplication and measurable things, always in some sense end up saying the result is trivial for open sets and measurable sets are close to open sets. Now you may have to work incredibly hard to work out what close to means. In fact, in this case here we have to, this one's quite easy, this one's pretty hard, being measurable, but it's only hard if you have to work out what the sense of close to measurable is. So I know of no example of a theorem with plus or times and measurable colorings where at the end of the proof you think, yes, great, how interesting. You always think, oh, yawn, it's because you're close to open. So I think that might look a nice result. It is quite a nice result, but I think it's quite a boring result somehow. And I think we're fascinated to know what happens to the reals in general. So is it true that you get x plus x monochromatic or not? And also this thing, can you go beyond the reals even? Could be true, but no substitute in ZFC, could that be true? And we think it probably isn't, we really have no idea. So I'll stop early, I'll stop there.
Right, so some questions? Yeah. Does that result you just said with the measurability of Baire property, does that use any form of the axiom of choice? In other words, would it be true in a model of determinacy then? So,
it certainly uses dependent choice. Does it only use dependent choice? I'm sorry, countable dependent. Does it? You're saying yeah.
So is that result true in a model determinacy then?
I don't know. We certainly. I don't know because we use lots of dependent countable choice, but I don't. I think it's probably all we use. So yeah, probably yes. That's probably all we use. Yeah.
Do you have any, in measurable and property bear, the two senses have been close to open. Are there any kind of ideals on the reals where you say you're close to open if the symmetric difference is in this ideal? Have you looked at other ideals besides null and meager?
No.
Okay.
So I don't know what happened there. But what would we love to be if we could find such an ideal where the answer was a yes, but for an interesting reason. That'd be brilliant. Yeah.
Actually, it's more than a question. It's actually a remark in a very vague analogy. Is there are quite a number of constructions where you can get bad examples for the aleph n, which are in some sense pump up. You take an example of aleph n, you can pump it to aleph n plus 1, when the process stops at aleph omega, that you can't, this pump up thing that doesn't work anymore. It's typical questions about freeness of groups and stuff like that. There's some certain examples. So it's just a vague analogy. I don't know whether it's relevant for this.
That's very interesting. I don't know.
Really, for instance, if you talk set theoretically, typically what you use is the fact that at aleph n plus 1, there exists a stationary set that doesn't reflect. I mean, this is typical dose of cofinality, and then aleph omega plus 1, you lost it. So again, I don't know whether it's relevant, but
For us, it's almost, for us, even getting to this is somehow accidental, somehow good luck to even get to here somehow. It just came that you happen to bound those, but I don't know. There are similar things. There are things, maybe similar to what you're saying. There are things where you're looking for a graph with an unfriendly partition, and there are things where the proof you want to do breaks down aleph omega, and there are counterexamples there. So yeah, so maybe, and yeah, it did cross our minds about false aleph omega, but we couldn't.
I'll give you an example. Consider the fact of existence of transversal. Namely, so suppose you have, for a regular cardinal, suppose you have a family of countable sets, such that every smaller cardinality subset has a one-to-one choice function, a transversal, but the whole family does not. If you have an example at kappa, you can pump it up to example at kappa plus, provided kappa is regular, but it stops.
So maybe it is false at aleph omega. We tried to find some colorings that were bad there, and we definitely couldn't. But probably weren't being clever enough. So I don't know. Yeah, you might well be right. It'll be very, very interesting. If it stopped working there, it'd be amazingly interesting, actually.
Yes. Some other questions? I mean, could you explain a bit the other counterexample you mentioned, why it doesn't work for, which doesn't work for Q, worked for Q but doesn't work for N?
Yeah, I'll tell you what the system is. It takes a second to write out. So the system will have some x's, some y's, and a special thing called z. So the following system is definitely not PR over the rationals. This is a bad system. You insist that x1 minus y1, there's a difference that's z. There's another difference that's half z. Another difference that's a quarter z, and so on. Now it turns out asking for differences, so this being monochromatic says you have some z that's, let's say, red, 2 points that are z apart, which are both red, also 2z over 2 apart, z over 4 parts. This you can reckon the rationals. But weirdly, you can, actually, let me just write it like this instead, I'm sorry. I'll put it that way instead. If you expand these with more variables, that's what works. So here's the final system. It's x1 minus y1 is z, then it's x11 plus x21 plus x22 minus y21 minus y22 is z. Then 4, so x31 plus x34 minus y31 plus y34 is z, and so on. So you've got lots of totally independent variables. And it's the difference of those two is this. The difference between those two and those two is the same thing. Those four. And it turns out that this system turns out eventually with some stuff on central sets, so some beta n type stuff is persuaded over Q, but you quite easily check it doesn't work over naturals. So that's the example. That's our only. We don't have a family. We have one example. Basically, that example or trivial modification. We don't have a general family of examples.
Right, so some other questions? Okay, so then let's just thank the speaker again.